In this video, we learn about set theory. Let's start with some basic definitions in set theory. A set is a well-defined collection of objects of the same kind. So the key feature of a set is that the objects must be well-defined and they should be of the same kind. A set is denoted by a capital letter and its element is written in curly braces. With our first example, we have the set A to be equal to 1, 3, 5, 7, and 9. Thus, A is a set of the first 5 odd numbers. So A is denoted in a capital letter and the elements are written in curly braces. Let's look at some types of sets. The first type is the null set or the empty set. So this set has no elements. So if set A is an empty set, then we are going to denote A by this phi symbol, or we can write A as the curly braces with no elements inside. The second type is the unit set. So a unit set has only one element. So in this example, we have A having an element of 2, and in the second example, we have A having the elements of the empty set. So this set is a unit set, but it's not an empty set because set A has one element, which is phi in this case. The next type of set is the universal set. So this is the whole set under consideration, right? That's the set of all the elements under discussion and is denoted by capital letter U. The next type of set is the subset. A is a subset of B if every element in A is also in B. Thus, if A is contained in B, then we say that A is a subset of B. Our next type of set is the equal set. A and B are said to be equal if they have the same elements. But here, we are talking about the same number of elements, but not how the elements are being arranged. So in this example, we have A having the elements of 1, 2, 4, and 6, and B having the elements of 6, 2, 4, and 1. So here, the arrangement of the elements in A is different from that of B, but since they have the same elements, we are going to say that A is equal to B, or A and B are equal sets. Our next type of set is the equivalent set. So two sets are said to be equivalent if they have the same cardinality or the same number of elements. We also have the infinite set. A set with infinitely many elements is said to be an infinite set. So when you take the set of the natural numbers, that's 1, 2, 3 up to infinity. Since this set has infinite elements, we say that the set of natural numbers is an infinite set. And we also have a finite set, that's a set with a finite number of elements. So set A having the elements 1, 2, 3, and 4 is said to be a finite set. Now we also have disjoint sets. Two sets A and B are said to be disjoint if they have no elements in common. So in this example, we have A to be 1, 2, 3, and 4, and B to be the set 5, 6, 7, and 8. So since A and B have no elements in common, we say that A and B are disjoint, or the intersection of A and B is the empty set. Operations of sets. There are three common operations on sets. The first one is the intersection, the next one is the union, and the complements of sets. Let's start with the intersection of sets. Let A and B be two sets. The set of elements that belong to both A and B is called the intersection of A and B. So in this Venn diagram, we have the sets A given as this guy and B given as this. The intersection of A and B is the shaded region. As the elements that are in both A and also in B. Union of sets. Let A and B be two sets. The union of A and B is the set obtained by putting together the elements of A and B. And we denote the union by this symbol, which looks like U. So in this example, we have A union B given by the shaded region. That's when we sum the elements, or when we put together all the elements of A and B, we are going to have this shaded region. So the union is simply the elements that are in either A or B. The next operation is the complement of sets, denoted by prime. Let B be a subset of A. The complement of B relative to A is the set of elements in A that are not in B. This is written as B prime subscript A. We can also write it as A minus B. That's when we take the element of B out of A, what will be left is B complement relative to A. So here we have the set A given by this whole area, B given by this area. And so when we take B out of A, we are going to be left with the shaded region in light yellow. So we call this region B complements relative to A. We now consider some identities in set theory. Let P, Q, and R be sets, and let U be the universal set. Then the following hold. The first one is the commutative law. That's P union Q is the same as Q union P, and P intersection Q is the same as Q intersection B. The next one is the associative laws. Thus, P union into brackets Q union R is the same as P union Q into brackets all union R. And also P intersection into brackets Q intersection R is the same as P intersection Q all in one brackets all intersection R. The third one is the distributive laws. The fourth one is P minus Q. That's the complement of Q is equal to P intersection Q complement. And the fifth one is if P is a subset of Q, then Q complement is a subset of P complement. The sixth one is P union the empty set is equal to P, and P intersection the empty set is equal to the empty set. The seventh one is P union the universal set is equal to the universal set, and P intersection the universal set is equal to P. The eighth one is the De Morgan's law. The first law says that P union Q or complement is equal to P complement intersection Q complement. And the second De Morgan's law is P intersection Q or complement is equal to P complement union Q complement. Let's solve some examples using these identities in set terms. In this example, we have set P, Q, and R, and we have to verify the following. Number one, we have to verify that P intersection Q is the same as Q intersection P. Number two, we have to verify that Q minus P, that's P complement relative to Q, is equal to Q intersection P complement. And the third one is the De Morgan's law. The first one is P union Q or complement is the same as P complement intersection Q complement. And the second one is P intersection Q or complement is the same as P complement union Q complement. And the fourth one is to verify if P union the universal set is equal to the universal set U, and also P intersection the universal set U is equal to P. And the last one is to verify if P is a subset of Q, then Q complement is a subset of P. To solve this example, we need to first find the universal set. So that's when we put all these sets together, what are we going to have? So the universal set U will be given us 1, 2, 3, 4, 5. So we don't have 6 in any of these sets. So we are going to move on to 7. Then we go to 8, then 9. This is equal to P union Q union R. Let's compute P complement. Now P complement is the set of all the elements that are in the universal set, but that are not in the set P. And so you're going to have the set 1. So 2 is in P, then 3, 4. So you're going to have 5. Then we have 8 and 9. Also, Q complement is the set of elements that are in the universal set, but that's not in Q. And so we are going to have, so we have 1, 2, 3, 4, 5, 7, 9. So the only element is 8. Now let's compute R complement. So for R complement, you're going to have 1, 3, 5, and 7. With our first question, we have to verify that P intersection Q is equal to Q intersection P. We have the set P and Q giving us these guys. So we are going to find the elements that are in both P and Q. And so from these guys, we have the elements 2, 3, 4, and 7. And these elements are also in the set Q. And so we are going to have P intersection Q to be the set of elements 2, 3, 4, and 7 because these elements are in both sets. So our results will be giving us 2, 3, 4, and 7. Also, let's compute Q intersection P. That's the elements that are in both Q and P. So you're going to have the elements 2, 3, 4, and 7 to be in both P and Q. And so our results will be giving us 2, 3, 4, and 7. And so from here, we can see that P intersection Q is equal to Q intersection P. That's the first theorem has been verified. With the second question, you have to verify that Q minus P, that's the complement of P relative to Q, is equal to Q intersection P complement. Now let's find Q minus P. That's the elements in Q that are not in P. So here we are going to have the elements in Q that are not in P to be giving us 1, 5, and 9. So we are going to have our results to be equal to 1, 5, and 9. Now let's compute Q intersection P complement. So we have the set Q giving us this guy and P complement giving us this guy. And so the elements that are in both Q and P complement will be giving us, so we have 1 here, 1 here, we have 5 here, 5 here, we also have 9 here, 9 here. So our result is going to be 1, 5, and 9. Now let's see if our result is true. So we are going to have Q minus P to be equal to 1, 5, and 9. And also Q intersection P complement is equal to 1, 5, and 9. And so the second theorem has also been verified. With our next example, we have to verify the De Morgan's law. Now let's start with the first law. So let's compute P union Q. So P union Q is the set of elements we get when we combine P and Q. So combining P and Q, we are going to have 1, 2, 3, 4, 5, 7, and 9. So let's compute P union Q complement. That's the set of elements that's in the universal set, but that's not in P union Q. So as you can see, the set of elements that's in U and not in P union Q will be the element 8. So you're going to have this to be the unit set 8. The next step is to compute P complements intersection Q complements. So that's the sets of elements that's in both P complements and Q complements. So here we have P complements here and Q complements here. Elements that is in both P complements and Q complements is going to be 8. So we are going to have our intersection to be the element 8. And so here, as we can see, we have P union Q or complement to be equal to P complement intersection Q complement, which is equal to the unit set 8. We now verify the second law of the De Morgan's law. So that's, we have to verify that P intersection Q or complement is equal to P complement union Q complement. Now let's compute P intersection Q. That's the set of elements that are in both P and Q. So we have P given here and Q given here. So the set of elements that are in both P and Q will be giving us 2, 3, 4, and 7. So we're going to have our sets to be 2, 3, 4, and 7. Now let's compute P intersection Q or complement. That's the set of elements that are in P intersection Q, but not in the universal set U. And so we are going to have the set of elements to be 1, 5, 8, and 9. So our set is going to be 1, 5, 8, and 9. We now compute P complement union Q complement. That's when we put together the set of elements in P complement and Q complement. And so we are going to have our results to be equal to 1, 5, 8, and 9. And so as we can see, we have P intersection Q or complement to be equal to P complement union Q complement, which is equal to 1, 5, 8, and 9. And so we've been able to verify the two laws of the De Morgan's property. You guys should try and answer on question 4. So let me solve number 5. With number 5, we are told that if P is a subset of Q, then Q complement is a subset of P complement. So the first step is to ask yourself, is P a subset of Q? So now let's see if P is a subset of Q. Thus, are the elements in P contained in Q? And here we can see that Q contains all the elements in P, right? And so here we can say that P is contained in Q. So the first condition is met. Then let's see if Q complement will be a subset of P complement. So from this guy, we have P complement to be equal to 1, 5, 8, and 9, and Q complement to be equal to 8. And so we can see that Q complement is a subset of P complement. And so we've been able to verify the fifth set theorem. Thank you guys for watching. See you guys in the next video. Bye.